So thank you for completing the module 3 initial attempt of your assessment. On the whole, the class average was a 60 and students used 36 minutes out of 60 available minutes. So I don't know if students felt rushed. It was a shorter quiz. There were 14 questions, right? So they'd be worth larger point values, right? In terms of difficulty rating, 5 were considered easy, 1 was considered hard, and 8 were considered medium difficulty questions, which is a pretty decent mix. There were some that students all answered correctly or incorrectly in the same manner, so they were flagged as poor or cannot calculate questions in terms of student discrimination. What we're going to do now is start with the items that pose the greatest challenge for students. And I'm also going to print a copy of this just so we have it for posterity. We'll go ahead and post the reconciliation after our review, and we will pivot and take a look at a couple of related issues very quickly. Does anyone have any questions before we begin? Hearing none, let's make the screen a little bigger. Can everybody see the screen?
Yes.
Okay. So this multiple answer question posed the greatest challenge for all of our students. You are told to use logic gate combinations to implement a custom hardware solution. One of the design requirements is to ensure the behavior of the solution is true for most input scenarios, but also false for a significant number of scenarios, right? Choose the best options that will accomplish this goal using a minimum number of logic gates. This gets back to a review we had of the casino scenario. Does everyone remember the 2 diagrams for the casino scenario?
Yeah.
Okay, so if you use mostly OR logic gates and some AND logic gates, you get that behavior. You have more trues because ORs will be true more often, ANDs less so. Does everybody understand why this answer choice is desirable?
Yeah.
Okay. Then when we say devise a serial arrangement of OR logic gates first, what we're saying is that we're going to, when we say serial arrangement, we're saying that the ORs have multiple inputs. Instead of 2 input ORs in parallel, we have only a couple of ORs, like the casino scenario on the right, where an OR with 4 inputs or 8 inputs, that's actually 2 input ORs in a series. Does everybody understand what I'm talking about there? Maybe, kind of, sort of. Here, everybody's kind of quiet. So I'm thinking, yeah, we're not as let's see, the casino example was in module 2. Let's dial that up here. Ordinarily, at its most rudimentary or basic level, ands and ors have 2 inputs, right? Same thing with NANDs and NORs, XORs and XNORs. So on a very basic level, on the lowest level, these components have two inputs. If you stitch them together in series, where the output of the first one feeds into one of the inputs of the next one, what you have, in a sense, is the same animal with multiple inputs. So when we talk about a serial arrangement, what we're saying, where is that? Addendum. The casino. Where's the casino example? Was that in module 4?
I think it was module 3.
I don't think it was module 3 too. We had it. Module 3. That's module 4. There. So these are the images themselves. This kind of an arrangement would be referred to as a parallel structure, right? Because we have two input ANDs and they're connected in a manner where you have two input AND alongside a two input AND, alongside a two input AND, alongside a two input AND. That is referred to as a parallel. That's a parallel arrangement, right? So you have an AND, an AND, an AND, an AND. They're next to each other. They're in parallel. When you're in series, you have a 4-input AND. And what this is inside is actually a 2-input AND that feeds in series into another 2-input AND with the C input that feeds into a third 2-input AND, right? So the ANDs are in series. That's what we mean by this. Okay. So when we say something is arranged in series, that's another way of stating that we have logic gates that have multiple inputs, more than 2 inputs, right? So this is a parallel arrangement. ANDs are configured in a series, right? And as you do this, what's happening is that you're turning up or turning down the instance of occurrence based on which logic gate you're putting in first, okay? So I know this is a little complex, but in our scenario for the assessment, the interest is that we want it to be true most of the time, but we still want a significant number of we want a significant number of falses in the mix. That means we don't want an absolute case. We don't want absolute truths all the time, except for one extreme case where everything is false. If we have a mix of falses, that means we're moderating the number of falses that are likely based on the construction. Does that make sense? So in the casino example, when we do things in parallel, the behavior of that logic gate is expressed more strongly. In this case, the AND, right? The number of ANDs that require, I mean, basically ANDs, unless everything is true, ANDs don't trigger a true. But if you use series, you're turning down the strength level of the ANDs. In this case, AND is expressed more prominently. In this case, OR is expressed less prominently. I mean, AND is expressed less prominently. Does that make sense? Kind of, sort of. So what are we looking for? We're looking for this, except that you have ORs here and you have an AND here. You have a case, let's repeat that. Some of the times we want them to be false, right? So you're devising a serial arrangement of ORs. Now, most students said use mostly AND logic gates and some OR logic gates. Devise a serial arrangement of AND logic gates first. So why are these not the case? Most of the time we want it to be true. In the casino example, most of the time it's not true. It's only true a few times, right? So instead of using ands, we're using ors. We're flipping it. We're doing the reverse scenario of what the casino, it's like the casino issue here, except ors are here and ands are here. Are there any questions about this?
No.
I think what happened here is that students went, oh, this looks like the casino thing. And then they intuitively chose these two answers. And that would be correct if one of the design requirements is to ensure the behavior of the solution is false for most inputs, but also true for a significant number of scenarios. And in that case, you'd be dealing with this one, right? As opposed to this one. And there's a 1 in 8 chance. But here, well, all right. So depending on the scenario, right? In any case, the thing to key into is the idea of what's most prominent. That's your first logic gate. And is it like an absolute case except for one extreme? Or is there a good mix of other outputs, right? So that's the pattern we want you to fix on. And in the retake, in your final attempt, you'll have a chance to take another shot at this multi-answer question. Are there any questions or concerns about this one before we move on? I know we took quite a while to explain that, but I wanted to be sure everybody was up on it. Alrighty. A multiple choice or item posed significant challenges for many students. The multiple choice item reads, it has been said that an XNOR with many inputs is ideally suited to detect what? And the correct answer is if all of the inputs are the same. Which logic gate detects differences? Say again. That's muffled. I can't hear what you're saying.
He said Michael was saying XOR.
XOR is correct. Thank you. So if the question reads differently, it has been said that an XOR with many inputs is ideally suited to detect what? That would be the first answer. So XOR would be the first answer, right? XNOR is the second answer. If the inputs are all the same, all zeros or all ones. The key to remember is that we're talking about whether they're different or the same with XOR or XNOR. It's not what their values are, it's whether or not all the values are the same. So all the inputs can be 0 or all the inputs can be 1, and an XNOR will post a true in either of those cases. If any of the inputs are different whatsoever on the truth table, an XOR will post a true. Okay. Moving right along. HDL input order, right? True or false? A diagram shows an input order for logic gates to be C and A for the first logic gate. And B is an input for the last logic gate. The order these are listed in the HDL statement for N does matter. It will not run and load correctly if the HDL order does not match the diagram order. In a case like this, where A and C are used for the first logic gate, that is a correct statement. Generically, in the HDL simulation environment, the order that you list logic gate statements does not usually matter. But what's happened here is that there's a custom built where different inputs must be handled first. And in order for that output to then function with a B input for the next logic gate, right? This one has to happen first. So when you're looking at the Boolean function statement, what you're seeing are parentheses that require the first operation with C and A first. It's an order of operations issue, right? So now, in most cases, the order does not matter. And I'm going to take a second look at this just to be sure, but I'm going to go ahead and create a diagram and then run it and make sure. The intent of this question was to specify that there's a custom departure that's forced when you get a Boolean function where there are parentheses and there's an order of operations that's different. In that case, it's important for the HDL. It's important for the logic to reflect that. And there are cases, special cases, except for special cases, the order doesn't matter, but in special cases where things are intentionally executed in a different manner, then there are accommodations that have to occur. So most of the time it's false. When we go to the trouble to explain there's something unusual going on here, that's your first clue that, okay, there could be a difference here. Are there any questions about what I've explained?
You were saying that most times it's false?
Most of the time, the order of the listing in the HDL code doesn't matter. So long as you're dealing with basic components and basic inputs. But what's going on is that we have a custom logic gate and we've gone out of our way to call out C and A. And then there's another logic gate that follows, right? So the inputs for C and A have to be executed initially in order for the B input to function properly. So there, put another way, there are special cases or exceptions to the general rule that order doesn't matter.
Oh,
Okay, does that help?
yeah.
Okay. And if you have a question where I'm calling out something that's peculiar and different, that's your first clue that, okay, you know, there are always exceptions, right? There are absolutes, but saying that like case sensitivity doesn't matter in the HDL simulator environment. Oh yeah, it does. There are special cases where case sensitivity, for some reason or another, if case sensitivity isn't honored, it isn't expressed in a very specific way, you won't get that logic gate simulation to run no matter what you do. And that's frustrating. But so I've had to assist students with solutions and they're like, I don't get why this isn't working. And it's a head scratcher for me too. And I'm like, okay, let's try this. Let's change the case sensitivity of the components that are listed just to see. Let's make sure it's consistent with what they're doing in the demos for the simulator. And sure enough, it works. It's like, well, it's not supposed to matter. They say it doesn't matter. Yeah, it does. Sometimes it does. And the only way you'll get it to work is if you make an adjustment that way. Mux selector input. So multiple choice. This was an item that posed a challenge for some students. It reads, the selector input A of a mux digital component with two other input sources, input I sub 0 and I sub 1, is receiving the following repeating binary values. 1 0 1 0 1 0 1 0. What will result from this selector input? Now, a good number of our students chose the correct answer. Each value selects back and forth between the other source inputs, I sub 0 and I sub 1. So if you have two inputs and they're each receiving different inputs, right? And the MUX input selector A is in the mix, then when that toggles back and forth, you get 1 0 1 0 1 0. I think what we can do is, for the final attempt of this module assessment, I think we're going to add additional detail to explain a little further and say two other input sources, I sub 0 and I sub 1, that receive the same input value in each case. The same but different. And that, all right, so if you clarify that, that could be confusing. We'll tweak the wording and I'll revise this question for the final attempt so that there's better clarity. But what you'll understand is that I sub 0 has the same input value all the time. I sub 1 has the same input value all the time, but the input values for I sub 0 and I sub 1 are different, right? And they're repeating, okay? Well, in a binary world, you only have two values, off and on, right? Does everybody understand that?
Yeah.
Binary, right? It's not a hex value where we have 16 different values, 0 through F. It's binary, so it's only 1 or only 0. And we'll clarify for this question a little differently. Does anyone have any questions about this item? Okay. Which logic gate? So once we get to this tipping point right here, each item is worth 1/4 of a point. Nearly everyone got this one done, correctly. We'll review this one and then we'll look down here to see if there's the ordering item. We'll review multiple answer here, could have been better, and multiple answer here. If anyone wants to see any of these other ones, we can, but here, multiple choice cannot calculate. The points possible was 1/4 point, and the average for the class was 1/4 point. That means everybody got this one correct, right? So we're not gonna review that one. But if there's any other ones you want to review that were close, we'll take a look. So diagram H below represents the operation of a special compound logic. There should be a diagram in the resources folder in the material and in the links on the website to this kind of thing, right? So this diagram should be no stranger to any of you because it's in the resources, and I don't think we called out this example in particular regularly, but I think we were glossing around when it came to MUX and DMUX. That might have been in there, but it was also in links to other websites, and it was also on other screens. All right, so which logic gate operates in this management, in this instance? What you see here is a case where A is selected, then B is selected, then C is selected, then D is selected. So your inputs are being selected. Well, that's the behavior of a MUX in so many words. Does everybody see how, all right, in the first case, A is working, then B is working, then C is working, then D is working?
Yeah.
Okay. And with those different inputs, you see how you get other inputs. So this is the selector input, right? you're triggering, no, I'm sorry, these are the selector inputs. So by choosing 0, 0, 0, 1, 1, 0, or 1, 1, these are the selector inputs that are operating. There's just 2 of them. Let's repeat that. In the basic mux example, we had a single selector input. When you start working with multiplexers and demultiplexers, and there's many more inputs, you can have more selector inputs to allow for a greater number of input selection. So instead of just having 1 selector input, we have 2. And if we have two possible combinations of inputs, we can do a truth table for that, right? So it's 0, 0, 0, 1, 1, 0, or 1, 1. That's literally a 2 input truth table. Does everybody understand what I'm saying? So what happens is if both A and B are 0, we're using A. If A is 1 and B is 0, we're using B. If B is 1 and A is 0, we're using C. And if A and B are both 1, we're using D. So I know this is kind of a wrinkle, but it's a different representation of what a mux is all about. Any questions?
No.
Okay. It's pretty cool stuff. I mean, when you think about it and you look at it, and most students did get that right, but a fair number, about a quarter of the students didn't. So that's why we went over that, okay? We want to close the loop. Let's look at our ordering. I'm going to skip over these unless someone says, hey, I want to see that one. Like I want to see the wiring circuit one. Is there anybody that wants to see any of these questions? Because most folks got this right. It's cool for me to explain things, even if everyone got it right. That's fine. And if you say, yeah, I want to see that, I'm not calling out who it is, and I'm not going to mention your name. So any takers? Going once, going twice? Okay. Here is an ordering
Give me
item.
the D.
I'm sorry, was that a question?
Yeah, about the demux.
About the
Best
demux?
way to the best way to describe it.
Okay. I need you to hold on a second. I gotta
Oh,
deal with something here. So we're gonna go back to the demux. This one. So the demultiplexer, right? Select the statement below that best describes the function of a demux compound logic gate. So demux is conceptually similar to a multiplexer. It just works differently. And what we're talking about is a case where the selector inputs switch between multiple outputs. So that's the case for a demux. Instead of it selects between multiple inputs, and that's a mux. The selector switches between outputs. So that's the answer for the demux logic gate. Whether or not this was a gibberish answer about XNOR using not, that was just a bogus. It was a bogus answer. We've never said anything about that in our resource material about that kind of business. I hope that answers the question about demux. Let's look at the ordering. So for the ordering, you are given an implementation of a diagram for a compound component made of simple gates. So you're handed a diagram. It is a compound component. That means that there are simple logic gates in a mix, and you have the diagram. And what kind is it? It's not an input diagram, it's an implementation diagram. So you're seeing the inside pieces of that of that creation, right? So we're creating something novel. What are the tasks you should follow to create the HDL and to run the prototype in a hardware simulator in the most efficient manner? Well, the first thing you want to do is you want to write out the Boolean function. And I know that may not be intuitive, but when you get a diagram and you're looking at it, if there's an order of operations based on the diagram, you want your Boolean function to reflect that, right? Then you do the truth table. Then you do the canonical. Then you state the logic plainly in pseudocode, okay? Any questions about this item in particular? Now, a lot of times you're given a Boolean function, and you may be asked to create a diagram based on a Boolean function. So you can be given a diagram and asked to create the Boolean function and everything else. In some cases, you're just given the Boolean function. You don't have a diagram, but you have to create a diagram, and then you go from there. So what am I saying? A diagram or Boolean function can be the reference used to start the creation process. Does everyone understand what I'm saying?
Yeah.
Yes.
Yeah. They give you a Boolean function, draw the diagram. They give you a diagram, come up with a Boolean function. When you start getting into more elegant creations, you got to start your tasks a little differently. All right, I'm going to handle the last two very quickly because we are running a little over and I want to be finished in time. Design scenario A. So this has to do with the casino example. You are tasked with devising hardware controls based upon logic and probability. Casino. You are told to increase the odds that a desired outcome will occur after a low number of trials. That's the left example of the casino. In your diagram, in the reference provided, it's the left side, right? So you have logic gates configured parallel versus serial. We've been over that. We're using AND logic gates first, and we're using more logic gates for input interfaces. So we're consuming more logic gates to provide inputs. That means we have more 2-input logic gates, not multiple input, fewer logic gates, like the right side. Does everybody understand that?
Yeah.
Okay. Last question. You are tasked with devising hardware controls based upon logic and probability. You are told to decrease the odds that a desired outcome will occur after a lower number of trials. Casino. It's the reverse. It's the right side we were talking about. The use of AND logic gates is first. Okay. Because, well, all right, just because in a casino, if you pulled a lever and it was true all the time, you'd be like, okay, the game is rigged and they're trying to hook us. Initial logic gates should be configured in serial versus in parallel. Use fewer logic gates for the input interfaces. So we use fewer logic gates, but that's because each logic gate has many more inputs, okay? I hope that makes sense. Any questions before we clear and post the reconciliation online? Okay. Please do complete the reconciliation promptly. We'll put the final attempt of your Module 3 assessment out there. Remember that if you haven't already completed the Module 2 retake, the final attempt of the Module 2 retake, you need to see about it right away. As soon as I put it out there. I thought I put it out there. Oh, no. Okay. Yeah, I'm going to put it out there. The Module 2 final attempt will be out there. And the reconciliation for Module 3. Any questions before we clear?